Hello and welcome to Physics with Amol sir. So this video is for class 12 and today we are going to see the effect of dielectrics on the capacitance of a parallel plate capacitor. Okay. So here you have a parallel plate capacitor. Right now there is no material put between the two plates. Okay. So there is a vacuum between the two plates of this capacitor. There is a charge plus Q on it. Okay. And we are going to assume there is a potential difference of V naught between the two plates. Okay. So in this derivation we are going to see what happens when we are inserting a dielectric between the two plates. Okay. So let's start. Alright. So without any dielectric material, okay, when there is a vacuum between the two plates, the capacitance is given by the symbol C naught. Okay. And C naught we will write as Q upon V naught. And this we will call as our equation number first. This you will see is already derived in our first part. So C naught we write as Q by V naught. Okay. And we already know that C naught is equal to epsilon naught A by D, where A is the area of the plates and D is the distance between the two plates. Fine. This we will call as our equation number second. Now let us see what happens when we are inserting a dielectric material. So we will insert a dielectric material between the two plates of the capacitor. When we have put a dielectric material, there is going to be polarization, as we have already seen. Okay. Because of that polarization, the electric field between the dielectric, between the parallel plates is going to change. Now, the electric field will become E is equal to sigma minus sigma P by epsilon naught. This sigma P denotes surface charge density on the dielectric material. Okay, so you will get E is equal to sigma minus sigma P by epsilon naught. Okay, and we can write sigma minus sigma P is equal to sigma by capital K. Why we are writing this, I will tell you. We are assuming that sigma minus sigma P is directly proportional to sigma. That is the change, the resultant charge density is directly proportional to the original charge density. This we can assume because this is a linear isotropic dielectric material that we have put inside. So using this, our equation for E can be written as, I will write it here. We can write it as E is equal to sigma by epsilon naught into K, and that we can call as our equation number 3. Okay, so you can write electric field as sigma upon epsilon naught into K. Moving on, if V is a potential difference between the plates now after the dielectric has been put, we can write E is equal to V upon D. Okay, that is electric field is potential per unit distance, or you will write V is equal to E into D. Fine. And then for this E, you can use the equation number 3 once again. What you will get? You will get V is equal to sigma D upon epsilon naught into K. This becomes equation number 4. Okay, so we can write equation 4 as V is equal to sigma D upon epsilon naught K. The value for potential difference can be given by sigma D by epsilon naught K. I will write it here. Okay, so V becomes equal to sigma D by epsilon naught K. That is equation number 4. This is equation 4. V is equal to sigma D by epsilon naught K. We can write sigma as Q upon A. Why Q upon A? That is the formula for sigma, charge per unit area. So I can write equation 4 as V is equal to Q into D upon epsilon naught K by A, and call this as equation number 5. Okay, how we got this? In place of sigma you have written it as Q by A, and that becomes our equation 5. Now, the capacitance of this particular capacitor, that will be given by capital C. Okay. So when the dielectric material has been put, capacitance C now becomes Q by V. This V is given by equation number 5. So we can write C is equal to Q upon QD epsilon naught Ka. Okay, I'm sure you understand how we got this particular equation. In place of V, you have put equation number 5. Then this Q will get cancelled and you will get C is equal to epsilon naught Ka by D. This is the formula for capacitance of a parallel plate capacitor with a dielectric material. So this is our required formula. C is equal to epsilon naught K into A by D. This formula gives you what will happen to the capacitance if we are putting a dielectric material between them. You can see that K is positive, and because K is positive, whenever you are putting a dielectric material, the capacitance increases. Okay, so that is the significance of this particular derivation. It tells us that to increase capacitance, we can put a dielectric material. Now let us talk about this factor K. Okay, we have seen that epsilon, okay, if this is the permittivity of that material. Okay, so we can write epsilon is equal to epsilon naught into capital K, and you can write K is equal to epsilon by epsilon naught. Is called as the dielectric constant of that material. Okay, the dielectric material that you have put, okay, so it is property of that particular material, and K we get as epsilon by epsilon naught. So I hope this derivation was understood. It might look like a lengthy derivation, but please ensure that you have understood it because it is a very important part. Okay, to understand dielectrics and to understand the effect of dielectrics on capacitors, this derivation is extremely important. Okay, and what we have learned from this is whenever you put a dielectric material between a parallel plates of capacitor, the capacitance increases. Okay, so this formula is important and the derivation also is very important. So make sure that you go through the derivation. If there are still more doubts, make sure that you are asking. Thank you.